My name is Arjun Roy, and I will be talking about fault management inside the data center space. So this represents work done at UCSD with my advisor, Alex Noren, and we also had the opportunity to validate this in a production Facebook data center environment. I'd like to thank my Facebook co-authors, James Zhang and Jasmeet Bugga. A little bit of background about this work. Back in 2012, I was an intern at Facebook, and my intern project that summer involved looking at the TCP metrics that we collected at the end hosts inside of the network. And during the course of that summer, I had a conversation with an engineer at Facebook. He mentioned that, every so often we'd see TCP retransmits, and it would be nice to figure out which link in the network was responsible for causing these retransmits. This is a paraphrase statement, but it's a conversation that I had. And the thing that makes it complicated in a data center network is that there's a lot of paths in the network that flows might communicate over, so you don't necessarily know where in the network your pain point is. And in addition to this, the scale of a large data center network means that since the number of components is large, and since the failure rate for these components is non-zero, that it's entirely possible that packet loss that you see in the network is actually due to a network fault. So suppose a link was to have a fault in the network, say from the core layer to the aggregation layer. In an ideal world, the endpoints connected to this link would realize that there's a fault and be able to raise a targeted alarm that would then flag it so you could fix it. In practice, however, there is an important class of fault that I term partial faults. Other people term them as gray faults, where a fault on the link might only impact a subset of the traffic flowing through the link at intermittent periods of time. This confounds both detecting whether a fault is happening as well as localizing specifically where in the network the fault is occurring. So our goal today will be to see if a partial fault occurs, can we narrow down exactly which link it is in a manner that's quick. Now, these gray faults have a variety of ways that they might occur. So recent literature talks about some of them. This could be due to dirty optical connectors. This could be due to TCAM bit errors or misconfigurations. And the salient point for this list is that it's a large, diverse list and that is likely to increase in size in the future. Maybe we stretch our optical cables too much, and that induces faults. So now there is a vast body of prior work that deals with fault management for data centers. This is just a listing over here. It talks about some of the different strategies people have used. And all of these strategies have to contend with the scale of the data center environment, both in terms of how many links there are, but also in terms of how many different kinds of applications there are and how much traffic that they send. Now, my argument today is that for a certain class of data centers, this scale can actually help us both detect and localize faults. Specifically, a significant amount of engineering effort has gone into providing really good load balancing for data center applications. So I reproduce a graph here from a prior work of mine a couple of years ago characterizing the traffic patterns inside Facebook's data centers. This is traffic from the point of view of a single Facebook cache server grouped by destination. And these distributions are very close to vertical, indicating a very even spread of traffic inside of this network. If we up-level our view to look at the entire cluster on a rack-to-rack basis, we see that the bulk of traffic is concentrated in these two orange bands going from the web servers in the network to the cache servers and vice versa. These bands have very even spread of traffic, no obvious hotspots. The hope over here is that this highly load balanced traffic can simplify fault handling. So hypothetically, these very evenly loaded paths in the network should mean that the per path performance is similar if there are no errors. And conversely, if there is an error, there should be outlier paths with worse performance than normal. So hypothetically, if we could find the network path for all the flows in the network, we could correlate the flow performance with the path through the network in order to find faults that occur. So this being an NSDI paper, today I will be talking about a system, the design and implementation thereof, that uses this approach to find and localize faults in a way that's application agnostic, in a way that doesn't have any additional probing overhead, and in a way that is more rapid than prior published works. So to start out with, we need the path information. This is a diagram depicting Facebook's current fabric data center topology. It's a fairly complicated diagram, though, so let's make it a little bit simpler. This is the same topology from the point of view of two communicating end hosts. The box is all the way on the edges, highlighted in red. And the switches that they use in order to communicate. So we want to find, for a given flow, the path to the network. We know the top of rack switches for free. There's only one. The topology is broken into 4 distinct planes of aggregation and core switches. So if we knew which core switch a flow traversed, we would essentially have the entire path resolved. So our solution is to install rules on the aggregation switches on each pod that marks packets based on which core downlink was traversed. So how do we use the path information now that we have it for essentially every flow inside the network? In principle, we could compare flow performance by path, but the problem is that we have a combinatorial explosion at this point. Just from a single host to all the destination rack, there is on the order of 10,000 paths that we need to consider. And second, this doesn't actually give us localization. It doesn't tell us which link along the path has a problem. Helpfully, however, for this traffic pattern, ECMP routing inside the network gives us not only an even distribution of flows per link, but also an even distribution of bytes per link. So we can just compare the links directly. So we define something called an equivalence set, a set of links inside the data center that handle nominally similar load and exhibit similar performance in the absence of faults. And this gives us 2 benefits. The first is it reduces the number of comparisons we need from on the order of tens of thousands to on the order of a few hundreds. The second is, by definition, it'll pinpoint a fault to the specific location. To give some intuition on what this might look like in the Facebook topology, here's a simplified version of the topology diagram. Now, we're only looking at a single host and the pod that it's in. The one equivalent set that we can form are the 4 uplinks from each top of rack switch to the pod aggregation layer. And it turns out that these have close to identical performance distribution in the absence of errors. Another equivalent set that one might form are the uplinks from the aggregation layer up to the core layer. And the same property applies. So now that we've talked about what the equivalent sets are, we need to talk about what metrics we're looking at. Now, the majority of the traffic inside this network is TCP, and the hosts will already track various metrics to do congestion control. This includes the congestion window and retransmits. Both are affected by packet loss that might occur. It includes the round trip time in case a delay is incurred inside the network. It turns out that network I/O system call is also a good predictor of traffic loss in some cases. Details will be in the paper for that. The caveat here is that it can be difficult to determine if an effect on one of these metrics is due to a faulty link, or if it's perhaps due to an overloaded host, or if it's due to application variance. But it turns out that with the equivalence set-based grouping, we can in fact not look at the individual metrics, but we can compare their distributions on a per link basis. And that when we do that, only link faults cause variance between the distributions for links. It turns out that the per application variance and the per host loading doesn't matter when we do this. So to demonstrate this in action, I demonstrate the equivalent set from the aggregation switch to the top of rack switch, the 4 links over here. And what we do is we install rules on the top of rack switch to mark packet DSCP based on which inbound link from the ag layer traffic used. This enables the host to aggregate TCP metrics by link. And what we do is we simulate an error on a single link using IP tables rules at that end host. The high-level thing that we're trying to show here is that for the 3 green links where there's no error, the distributions for the metrics that we've talked about are going to be very close to each other, but there's going to be a clear outlier for the faulty link. The fault rate here is 1 in 200 packets randomly dropped. So to depict the impact of the induced fault on the congestion window when we use the equivalent set formulation, I have a graph over here. It's a box and whisker plot. The x-axis is 4 categories, 1 for each link from the ag layer to the TOR. The y-axis is congestion window for all of the flows across that link in log scale. So the 3 categories on the right has a very degenerate box plot. The first and third quartiles are in fact close to identical, and the value is close to identical for all 3 of these links. But for the link with the fault induced, the distribution has shifted both in shape and in location, marking it as a clear outlier. Now the goal over here was hopefully that this would be application agnostic. I did this for a single cache server inside of the Facebook's data center, and now I reproduce this experiment for a web server. The high level here is that even though the shapes of the distributions involved and their locations are different, the outlier for the faulty link is still clear to pick out. And this is true for congestion window. It's also true for the TCP retransmits metric for this particular kind of fault. So now I've shown that for inducing a fault, an outlier results. But ideally, this would also occur for faults that would organically occur in production. So what we did is we monitored traffic through a pod aggregation switch without injecting any faults. And we collected this TCP metric data for 30 web server hosts. And these are production hosts. And we use as our equivalent set the 4 line cards connecting the aggregation switch to the core layer. Each line card has an equal number of links, and as a result, it's a valid comparison. Now, on the 25th of January, a single line card had a software fault. Specifically, the line card software controls BGP routing between it and the peers in the core layer. And this hung, so as a result, the BGP routes timed out. The bulk of the production traffic through that particular line card was routed away. A few minutes later, a production monitoring system at Facebook notices that the line cards aren't responding to pings and flags it as being faulty. Now, this fault was visible to our approach in about 30 seconds after the incidence of the software hang. So this graph over here depicts the congestion window on a per line card basis for all the flows traversing that line card for the 30 hosts that we monitored. The x-axis is seconds since the line card fault. So negative values on the left are going to be before the fault occurred. The y-axis is the mean congestion window for flows. There's 4 series. 3 of them are in black, correspond to the non-faulty line cards, and these stay very close to each other for the entire time. The red series corresponds to the line card where the software fault occurred. And right after the fault occurs and the bulk of traffic moves away, we see that the distribution for the statistics changes as the makeup of traffic across that line card changes dramatically. I'd like to stress that this is not us catching the fault, but catching the aftermath of the fault, showing that we can catch faults, but also more generally catch anomalies inside network statistics. So now, given that our equivalence set metric seems to have legs, we now need to figure out how to classify faulty links based on this information. So a question that we want to ask is, does this link, or this line card, or this other component in our set, have more retransmits per flow than the other elements in the set? A similar question that one might ask is, do 2 distributions have the same mean, or is one of them greater? Now, it turns out that there is a statistical test that one can use to answer this question. We use this as a classifier. We compare each link in our set to the other links in the set using the one sample student's t-test. So in principle, we could implement fault monitoring with this alone. We could set up a system where all of the end hosts look at their metrics, they have the path information, they run this t-test, and they figure out which links they think are faulty based on that. The downside here is that by itself, this is susceptible to false positives, which you can't afford when we're in a network that has on the orders of tens of thousands of links. So we have to account for these. Luckily, there's 2 things that will help us. The first is that we noted that these per host false positives were evenly distributed over the links that we were considering as time went on. And the second is that the data center has a very large number of hosts for which this observation holds true. So what we're trying to see is not if a given link has been marked faulty by a host, but what we're trying to do is once again perform outlier analysis. We want to ask, are all the links being marked faulty by hosts at similar, hopefully low rates, or are hosts flagging a particular subset of the links as faulty at higher rates? Once again, it turns out that there is a statistical test that we can use to answer just this question. It's the Chisquare test. It outputs a p-value ranging from 0 to 1. A p-value of close to 1 means that, yes, all of the links are being marked faulty by hosts at similar rates. A p-value close to 0 means that no, a subset of these links has a comparatively high percentage of hosts claiming that it is faulty. So what we do is we use this test as a centralized classifier. We aggregate the t-test-based information from all of the end hosts. We use the t-test classifier to determine if links are faulty or not from the point of view of a single end host, and then a controller running this chi-square test will then determine if the link is overall faulty or not based on this information. And we use a p-value of 0.05 as our cutoff for determining whether a link is bad or not. So now, given the description of our method, we have to evaluate this inside the data center. Now, the issue is that even though we were in a production data center, we're not a production monitoring system. We're a prototype system, so we had a small detection surface. We ended up not detecting any organic faults since we only had on the order of 100 hosts instrumented. Now, our approach was to inject simulated faults as described before. to evaluate the approach, and we had a variety of scenarios that we induced to see whether our system could keep up or not. This includes minuscule faults, faults with very low drop rates. It includes concurrent faults. It includes a masking fault where a relatively large fault might hide the effects of a smaller fault. And it includes correlated faults where a hardware fault can impact multiple links in close proximity. The details of all of these are in the paper. It turns out we only have time to talk about one of them today. So I'll focus on minuscule faults. So we took our network pod that we were instrumenting. We got 3 racks worth of production web server hosts that we installed this monitoring infrastructure on. We got a single aggregation switch that we installed our marking rules on. And for this experiment, we ignore the traffic that's flowing through the other aggregation switches. We use as our equivalent set the uplinks from the pod aggregation layer up to the core layer. And we choose one of these links, and we'll induce a partial fault on it of varying magnitude. So to begin with, I'm just going to describe the effectiveness of the per end host t-test when trying to find these faults. We vary the fault, the packet loss rate, from 2%, which is a very high number, to 0.1%, all the way down to 0.05% actually, to see what percentage of the end hosts that we'd instrumented would be able to catch and flag the fault in consecutive 10-second intervals. And it turns out that if the drop rate is 0.5% or higher, close to 100% will reliably flag that link as being faulty. But for drop rates that are lower than 0.5%, there is a linear drop-off in any given 10-second period of what percentage of hosts will actually flag it successfully. And this makes the job of the controller that's running the Chisquare test a little bit harder, since it needs to find a significant uptick in so-called faulty classifications for a given link from the end hosts in order to determine with confidence that the link is faulty. Now, one could potentially increase the number of hosts that are providing these classifications, which we can't do because we only have the 3 racks of hosts that we're looking at. Or we could instead leverage the fact that a fault is likely to continue in the next 10 seconds and the 10 seconds after that, and instead aggregate these classifications over time. So we can run the controller for a longer period of time and to build up more confidence that a particular link is faulty. So we have a trade-off here. We have a trade-off between how sensitive we are to detecting a fault versus how quickly we can determine if there is a fault. So we're going to describe what this trade-off looks like over here. The x-axis over here is the controller runtime in seconds. We go from 10 seconds all the way up to 3 minutes. The y-axis depicts the p-value that the chi-squared test running at the controller will output. You can see a dashed line here at 0.05 as being our cutoff. So if you're below that, that means the controller successfully caught the fault. And we depict the median, the 5th percentile, and the 95th percentile for what the controller output inside of our test. So as a sanity check, when there is no fault, the controller resolutely will output a value close to 1.0, regardless of what controller interval that we pick, which is good. That means that we avoid false positives. If we have a 0.25% link error, we see that for the 10-second controller interval case, the P95 is actually above our cutoff. So about 5% of the time, maybe a little bit more, we will miss the fault. But the rest of the time, we will successfully flag the fault. And if we go to a 20-second interval, then we reliably capture the fault in every 20-second interval. If we go to a 0.2% link error, we see that a 10-second controller interval is no longer sufficient to catch it. The p-value is significantly above that dotted line. But a 20-second interval, once again, suffices. As we go to a 0.15% link error and a 0.1% link error, we see the distribution start to shift to the right, indicating that the more slight the error is, the longer the controller needs to run in order to catch it. But even for a 0.1% link error, even for a 1 in 1,000 packet drop, upwards of 50% of the time, we can detect that a fault is occurring if we use a 2-minute interval. So now, in summary, I'd like to go back to the conversation that helped inspire this work to begin with. It turns out that for certain data center topologies with certain characteristics in the traffic, that it is in fact possible to figure out specifically which link in the network is the pain point for network anomalies that we might see. it turns out that we can use the scale of the network to allow us to do this in a way that is online and relatively lightweight, in a way that's application agnostic and doesn't require any additional probe traffic. Recently, I actually got the chance to talk once again to this engineer, saying that I had a paper that he might find interesting, and he reminded me that 2012 was a very long time ago. With that, I'd like to open it up to questions.
Right.
So Minglan Yu from Yale, and very interesting work. So your work depends on the assumption that ECMP is well balanced, but sometimes ECMP may get imbalanced. And if that happens, I wonder if your tool will output a large number of 40 links that may mislead the operators. I wonder how much you depend on this assumption, and how would you react when these things happen?
So one of the experiments that we ran actually was, this was not at Facebook, but this was on a private K=6 factory that we had at UCSD. We induced an ECMP imbalance kind of structurally inside of the network. And in that particular case, what our system caught was the imbalance. So in other words, let's say you have a set of n links that you ostensibly should be evenly balanced, and now an imbalance occurs such that one link is taking a lot more traffic. Our system ended up flagging that link as being, hey, the average over here is starting to suffer a little bit.
But the difficulty here is that imbalance will get propagated in many layers, so it's not easy. If it's just one layer, it's easy, but the cross layers might be harder. Yeah.
Yes, this is admittedly true, but we did not test for that in that particular case.
Okay. Thank you.
Right, thanks.
Hi, I'm Kang Shen from University of Michigan. I'm confused about your fault model. What faults are you assuming, and what's the detection mechanism? Because there is a big literature in fault-tolerant computing in the area. They have a definition of faults and errors. I'm totally confused. Can you define?
Sure. So there's two kinds of faults that I cared about when performing the study. The first is, so this is specifically faults affecting components inside of the network. The two things that we care about are we losing packets, and are packets getting delayed? And more specifically, I'm not talking about the case where a link goes down and all of the packets across it are lost and it stops forwarding traffic entirely, but specifically the case where, let's say that the link still reports itself as up, it's still shifting traffic, but occasionally a subset of traffic will get lost for some unknown reason. It might be due to just a dirty connector, it might be due to misconfiguration. That's kind of model number one. Model number two would be that traffic across a particular link is suffering from excessive delay. Not necessarily loss, but maybe queuing delay may be caused by misconfiguration. So we tested out both of those cases.
So you're talking about up or down or delay. That's a sort of timing fault. Okay? Mm-hmm. By the fault is a physical state of a malfunctioning state. Error is the consequence of a fault or manifestation of fault. Mm-hmm. And usually if you deal with the TCP, only a receiving host will know what's wrong with, right?
So
and how do you pinpoint which link is broken?
So the receiving host so in our experiment, the receiving host knows the entire path for the flow that's coming in. And as a result, since it sees that a certain link is having anomalous behavior, it can pinpoint that the fault might be occurring at that link.
We can talk offline. There are a lot of questions, though.
Sure, I'd be happy to answer questions offline.
Right, great. Xiao from the University of Washington. So, really nice work. Have you considered the effect of dynamic load balancing in the network, something like let it flow or Conga?
So far, I have not. So far, this is leveraging the fact that ECMP is a very commonly deployed load balancing architecture. But I would be happy to consider it in the future. But at the moment, I have no data regarding it.
Thank you.
Thanks. Hi, Dong Soo Han from KAIST. This type of systems usually produce meaningful result when it's run in production, right? So what are some of the challenges in deployment for your particular system? Does it induce a lot of overhead, or does it produce enough accuracy for it to be used in production?
The single hardest part of getting this work running is the fact that you need the path information for all of the flows inside the network. So The easiest way to do that would be for hypothetically, in an ideal world, could have whatever I want. It would be good if a switch had a rule that says that there's a certain set of bits inside the packet header, and the switch can arbitrarily write a value to that set of bits. Now, it turns out that switches are capable of doing this. They do, for example, do this to the DSCP field. The problem is that the DSCP field that we did in fact use for our prototype in this work has other uses. It's a relatively limited field of only 8 bits, and it does already have other meanings. If we had the ability to, say, do the same for the IPv6 flow label field, then we'd have 20 bits to work with, and we would be able to scale this up to the entire network. And that's basically the biggest challenge of getting into production, is being able to write to enough bits. There are other methods inside the paper for finding out path information in the absence of that particular capability. Those would mean that you can't do it for short flows. You would require flows to be long in order to figure out the path. So that would be the single biggest challenge.
Would a fault in your system affect traffic in production, though?
Sorry, could you repeat that, please?
Would a fault in your system in turn affect traffic in production?
So I have mentioned that we did monitor production systems, and the way that we induced a fault was to, at the end hosts that we're monitoring, if it went across a certain link that we wish to induce a fault on, we would have IP tables rules that drops the packet. And that means that production traffic is being impacted, but it's limited to only the hosts that we're monitoring. So Facebook was very gracious in allowing us to capture this data, but we didn't want to induce a fault inside the network core that affects all of the hosts in the network.
I had a different question, but we can talk offline. Thanks.
Okay.
All right, I think we have time for one last question.
Hi, great talk, Omid from Yale. So I'm wondering, it seems like that the Facebook data center, like the topology is such that you can identify the path of the packet by just looking at one switch. So do you think that your work is, does it extend to other type of data centers, or is it bound to Facebook by itself?
So, Sorry, please go ahead.
And the second question for me is that in data center, a lot of things are happening at the same time. So at any point in time, if you look at the data center, you might find a fault that relates to what you observed in your experiment. How did you make sure that it's not just luck, that what you see is what is happening in the data center?
Okay, so I'll answer the first question. So the paper does talk about alternative ways in order to figure out the path information. And this ends up being the hardest part of getting this sort of work running. And there is a way, for example, that would let you figure out, for an arbitrary topology, would let you figure out the path for the long flows, but then you would lose the information for the short flows. So potentially, depending on the traffic pattern that topology has, if enough of the flows were long flows, this would still be an applicable system. But if the majority of the flows are short flows and it's hard to figure out path information for short flows, that would be an example of a system of a network where this would be less applicable. I'm having a little bit of trouble understanding your second question.
So my second question is that how do you know what the error that you found is actually what is happening in the data center? Because at any point in time, if you say I have this fault, right, you can always map it to something that is happening in the data center.
Right. So the easiest way is there's graphs inside our paper that the way we experimented was we would induce a fault for a certain period of time, and then after a certain period of time has passed, we take the fault away. And every time we did that, there was a very clear correlation between our hosts say the link is fine, the hosts say the link is bad, and the hosts say the link is fine again. So there's two explanations. Either it's catching our fault, or something very, very unlikely happened. So I don't know if that satisfactorily answers your question.
Yeah, maybe we can take it offline.
All right.
But thank you.
All right, let's thank our speaker, Arjun.